Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Speakers. Next up after Michael will be Jochen. So, are you ready, Jochen?
Okay, we ready to go here? Great. Okay, so I'm going to go quickly through this. This is work we're doing in my group on a project called HiFi, which I'll explain in a second. Basic idea is that we view applications as a data management problem, and the way we're looking at this problem is to try to take techniques that were developed for this environment and to move them into a world that looks like this. Now, this is a pretty tall order, and a good way to get some energy in the community is to think about grand challenge applications. So everyone put up their applications. This isn't work that my group's done, unfortunately, but hopefully you'll see why this application has captured my imagination. This is from a paper in Pervasive 2005. I'll give you a second to think about it. And I know we're supposed to have pictures of our application, so here's one. There's actually better ones in the paper. But basically, we've got a microphone and a sensor on the door. And this actually is a good application for illustrating what I actually really want to talk about, which is we've got multimodal input. We do a bunch of data cleaning on it, and then we actually start processing it. Now, I don't have time to go over to the particular results of this paper, but just to show you, I find these all sort of vaguely disturbing is the word I was going to use. Anyway, we could talk about this over dinner if you like. Okay, so now what do I really want to talk about? What I really want to talk about is a system called HiFi, and it stands for High Fan-In. And the basic idea is we've actually seen this picture a number of times today without a name, and it's basically just saying that if you think about how you're going to build end-to-end sensor systems, so lots of sensors on the edges, and then there's going to be this natural funneling of information up from the edges of the network through various components of the rest of the environment. And in fact, as was already mentioned earlier, globally distributed sensor environments or sensor networks is actually not science fiction. They've existed for a long time. And if you think about Walmart, Walmart already does this with their point-of-sale systems. Okay, they're not doing it quite with RFID yet, but point of sale, they've been doing this for years. UPS, another company, sensors all over the place. They're tracking their trucks, telemetry from all the trucks. They know where all the packages are. They're getting barcode scans all over the world. Okay, so these types of systems exist today. Okay, and the data management problems that they bring about right now are only solved by the biggest companies, but eventually everybody's going to have to solve these. So what I want to talk about in the remaining 6 minutes that I have is basically saying, well, we have a lot of infrastructure here already, right? There's a lot of crusty old enterprise applications that run these businesses. Okay, now you're going to add in a bunch of new technology down at the bottom of this network, and as was already mentioned, this is stuff that's fundamentally different than what this software usually deals with, because unlike existing data entry systems, which are basically part of the virtual world, what these things are doing is measuring things from the physical world. And that brings in a lot of new challenges. And so what we propose is we want to come up with a level of abstraction or an API that's going to insulate all of this complex but very important enterprise software from these physical devices or vice versa. Okay? And we call this the virtual device layer or the device layer. Now, traditionally, in database systems have been tremendously successful in these enterprise environments for a number of reasons, but one of them is that they were built, at least relational database systems, were built with the notion of data independence, or some people like to call that abstraction. But there's two classical types of data independence in a relational database. There's logical data independence, which separates, protects the applications from changes to the underlying schema. So you put views between the schema and the applications so that you can adjust the way the database is logically structured. You don't have to change your applications. Physical data independence protects that logical structuring from changes at the physical level. So you can wheel in new disks, you can bring in new processors, you can move disk around, data around, you can add indexes and so on. So these exist today. And what we're arguing is that this is a new problem, okay? That you want to, this protection of the existing infrastructure from the physical devices requires a new type of data independence, and we call that metaphysical data independence. So you want independence from reality in some way, okay? So what can you do with a level of abstraction that gives you this kind of independence? You can do a lot of things. You can, you can hide errors. You can hide failures. You can do calibration. You can do sampling. All the things I have listed here. And in general, the way this picture looks is here's how things look today. You deploy your sensor network. You write an application for it, and you figure out how to do data cleaning, right? To take this messy data and turn it into something that's useful for your application. When you go to build the next application, you do that all over again. And what we're proposing is an architecture like this, where you have a level that does that for you, so that you can then build your applications on top of that. So we want to boost up the level of abstraction. We want to protect these applications from having to worry about these details. Okay? Now, here's a quick example. This isn't from the bathroom application. What we did here is we set up 2 shelves with boxes with RFID tags on them. We had 10 boxes on each shelf, and then we had 5 boxes on a cart. We moved them back and forth from one shelf to another. So you can see when you run the count, how many items are there on each shelf, it goes from 15 to 10 to 15 to 10 and so on. Okay? Now, what does it look like? What do you actually get out of the RFID readers? It looks like that. Okay? Now, if your business logic says, okay, restock every time the inventory goes below 5 items on a shelf, you can see you're going to be pretty busy. Okay? So you don't want to just take that raw RFID data and pipe it into the application. So what do? We have a pipeline of cleaning processes that we're able to run. They're actually, believe it or not, written as SQL queries. Okay? And this is a little bit of an eye test, but I'll just tell you briefly. Basically, you apply thresholding to individual items. You can then do smoothing over a time window. You can then actually look at multiple streams from different readers and either merge that or do arbitration. So this is actually a join, okay, in relational language. And then the most important one, or the one that a lot of people miss, is that in a lot of applications, you actually have data that tells you what's supposed to be happening. Okay, so a truck pulls up to a dock door. It's not a mystery what's on that truck. Okay, you've got an invoice or a manifest that tells you what's supposed to be there. So you start with that, and then you just do cross-checking against the database. Now, that's easy to do if the language that you're writing your cleaning in is a language that can deal with database data. Okay? So when you apply just some simple SQL processing to that dirty data stream you see, you don't get a perfect answer back, but certainly if that was your query, it would be good enough. Okay? Now, once you can do that, there's a whole bunch of things you can do, right? So once you define this level, there's a bunch of things you can do, including creating sensors that don't really exist by fusing information from heterogeneous sensors. It was already mentioned several times. You can track lineage information. You can bring up quality and confidence information. You can push a lot of the optimization down there. Talked about validation with external data. You can archive the data, which is important for a lot of applications. And you can also hide some of this messy, non-declarative programming stuff under that level. Okay, so just my last slide. So the basic idea is that we want to view large-scale sensor deployments as these high fan-in systems. And we're going to use, to the extent we can, query languages to build these systems because it's basically a data management problem, and query languages are good with dealing with lots of data. You can't just plug the sensors into your data management infrastructure, though, because they're different. Okay, they've got a lot of characteristics that those applications weren't built to deal with, and that's why you need a new level of data independence, which we kind of jokingly call metaphysical data independence. And I think with that, I will stop.
We do have about 2 or 3 minutes for questions, so please take questions.
Ooh.
I'll set up the next talk, though, while Mike's on.
Yes.
So from a detection perspective, you will be able to do better classifying if you know the context you're in. So there's some kind of connection down there you can find. So I'm not sure if in the database you're allowed to go for.
Yeah, so it's a good point. In the 2-hour version of this talk, I do get into that point. And so you do need a path. I was talking about bringing the data up from the edges up into the infrastructure, but there's a number of reasons why you actually need a communication path back down. One of them is to do this kind of validation that we talked about, where you want to push validation information out to the edges. Another is for actuation. Okay, and then a third thing that you need is for calibration and things like that. So for all those reasons, you do need a path that goes down from the infrastructure out to the edges as well. And that's part of the architecture. Is that?
Yeah, that's good. But that's really not usual, right, in the usual database.
Is it usual? Yeah, I mean, there was this thing called fjords that we worked on a while ago, which was all about push and pull and how you put them together. And so this problem's shown up in other places. But, you know, normally you don't think of database systems as being, you know, just this complete push of data from the bottom up to the top like that. So it's a little bit of a different environment. Yeah?
This could potentially be also applied, I would assume, to like an application like that Daniel presented, where you have different sensors and you could correlate.
Yeah, in fact, the one slide I skipped over was talking about this idea of virtual sensors, or soft sensors. And the idea is what we did there was we took RFID readers and we took sensor modes, little networks of sensor modes, and we, in a room about this big actually, we put in each corner an RFID reader and a little network of modes. We gave everybody who came into the room an RFID tag, and then we used the RFID to count the number of people in each area. We used the sensor network to measure the ambient sound level in that area, and then we just divided. So we looked for the part of the room that had the highest ratio of noise to people, and we called that the loudmouth sensor. So we were actually able to create, you know, a virtual sensor that lets you sense something that no individual physical sensor can do. And that's all hidden very nicely under that API. Okay, so I think I'm happy to talk to people over dinner.
We can talk later afterwards. Jochen, you're up next. If I could just get online to be ready to be next.
Okay, so the sound is fine, okay? Yeah, I can talk. Can you record? 1, 2, 3. Test, test, test. Which one? 5? Yeah. Oh. It's difficult to. Yes, yes, yeah. I can do this. 5, 4, 3, 2, 1. It's just difficult to understand from. Okay. So talk, 1, 2, 3. Okay, great. Okay, so the next 8 minutes, something about, someone called them Euro modes. Well, we just call them sensor nodes, and the figure looks quite familiar. So we started, let's say, 5 years ago with building our own sensor nodes, also for research, for education. We run into the same problems like everyone. We build gateways to Bluetooth, wireless LANs, etc., etc. And we developed a lot of software together with colleagues in Sweden, in France, in Belgium, etc., for flashing, for running TCP/IP on the nodes, even running a complete web server, different kinds of operating systems. We have NS2 simulation models, and this is all nice for research, for education, and it's all open source. You just look it up on the URL. You will find it there. But as soon as you want to go out into industry, you start with those dull components and dull applications. And you have to have, for example, certified nodes. You have to let them certify by some authority, FCC or the European rules, etc. And we looked especially in very low power, very long range, like 1.5 kilometers with a line of sight, 500 meters through buildings. So we can make sure they still work if there's a lot of interference. We have different kind of gateways, evaluation boards, etc. And these components, they look completely different. And why? Well, They are used for real applications, boring applications like building monitoring. In Sweden, there are some buildings, they want to see where they lose energy from heating. So the janitor just walks around and drops some sensor nodes, collects them after 3 months, and they know exactly the temperature in all the rooms. So kind of a boring application, a completely different application, but more or less the same nodes. We have with the Berlin firefighters, so we call this the Hansel and Gretel principle. They run to a building and they just drop sensor nodes every 10 meters or every 20 meters. And this is a real multi-hop case because you transmit some kind of personal health status over this multi-hop ad hoc network. There's no time for setting up the network. You just drop those nodes. And some guys from the medicine department, they developed sensors, measure the temperature inside the brain, because this gives you quite a good parameter for telling the commander outside, okay, this guy will stay there for another 5 minutes, 10 minutes, or let's get them out. So this is all the parameters are transmitted by an ad hoc wireless sensor network. Okay, so this is a broad range of different applications, but also some kind of fun applications. So our soccer-playing robots use the sensor network. This is very simple application, but it has to be very reliable. This is where we learned a lot about reliability, and now the second-time world champion in the soccer, this so-called small size league, was a championship in Japan. We also did something for home gateways. So we took a CE box and connected it to the wireless sensor network. And this is quite nice. It's very simple. Just connect it and you will receive an MMS on your mobile phone showing you what's going on at home as soon as there's some movement and you're lying on the beach somewhere in the Bahamas. So this was very simple from an integration point of view. But again, this application is not this kind of high reliability like you have for the firefighters. And as most of the groups, we have developed a lot of software. And sooner or later, we run into the problem how to integrate this with commercial tools. But it's nice to have some kind of a GUI for XP or CE, but who cares? You need some kind of integration. No engineer from chemical industry, whatever, will start to use your GUI. So we integrated, for example, our system into Softwire, visualstudio.net, which is quite nice. So with a single click and drop, you have an Excel integration. So it took us just basically 1 hour to integrate Excel spreadsheets, etc., into the wireless sensor networks, because the Softwire system already does everything for Lego programming, home automation, education, database, connectivity, etc., etc. So you just say, okay, this is the sensor, this is the gateway, now connect to some kind of Excel spreadsheet, and you have this kind of real-time data into your spreadsheet. So this is quite nice, just for demonstration. We also want to integrate tools like LabVIEW, for example. We also started some initial integration with the VRDK development kit, originally planned for robot control, and we will continue in this work. This will enable people to have some kind of very simple programming tool for this kind of sensor networks. Okay, if something happens here, then do this. Some things even kids can understand, or typically kids understand it quite faster. Okay, what did we do from a more scientific point of view? We developed real-time virtual machines adapted to sensor nodes. Very simple RISC architecture, small virtual machine, very small footprint, 160 kbyte, and the typical programs are just 1 kbyte. So if you want, you can download them over the air, also multi-hop, etc. And if something crashes, it doesn't matter. We have automatic watchdog and just kick out, flush the code from the sensor node. So nothing really serious happens. So real-time virtual machines. Another approach is a kind of a rule-based middleware architecture, because typically sensor networks, they're event-centric anyway. So there's event, triggers some kind of action. So we developed a language where you can program the nodes in a very, very simple way. You just tell the node, if this kind of event happens, then do this and this. Or if this event plus this event and this event, etc. happens, then do this and that. You can react to change of state. And then the workflow is basically very simple. You have some kind of fact repository, a lot of rules. You sleep 99.999% of the time. And then if something happens, you wake up the node, you process this rule, and then you check, Is there a new fact generated? You process the next rule. If there's no more rule to process, you just go to sleep again. It's very simple to exchange the rules. They're just some bytes, so you can do this over the air. It doesn't cost too much energy. So this is more research, and more industrial again is the integration into Visual Studio 2005. So basically, if you want to develop programs for this, you don't want to get used to some other programming language. So we developed some kind of a .NET plugin, and so you can program your sensor nodes C#. We developed a so-called Spot game combined .NET CPU with this programming environment. And if you're interested in the framework, just ask me later on. I can explain this a little bit more detail. And the very nice thing is you have all the IntelliSense and the dynamic help, the well-known programming models, because the sensor nodes are just objects. And you just say, OK, get me the neighborhood. And then while you do the programming, you can say, right mouse click, and then, OK, what's going on? What is the next command, etc. So very simple deployment. So to sum up, there's also a SensorNet platform in Europe with different kind of sensors for industrial use, for research. You can look this up on the web. We have some kind of integration activities, Visual Studio in this industrial automation system, building automation, and some programming activities like this kind of a tiny version of C#, graphical programming, rule-based architecture, real-time virtual machines, and started some parts of model-driven software development, combining embedded system software development and this kind of sensor node software development. Okay, thank you.
Any questions for Jochen?
I killed everyone. So I've got some of the notes over there, so we can play with it.
Take my question now. That's what to say.
Oh. Oh, sorry.
No problem. Okay. So if there's no questions in the room, then next up is online. Thank you very much.
Oh, yeah. Hello?
Yeah.
Okay. All right. Good afternoon. I'm giving this talk on behalf of my advisor, Dr. Roja, because he cannot come here since he just had his young baby. So in this talk, I will briefly introduce an integration environment, which is Kansai, that we have been developing at Ohio State. So originally, Kansai was developed was built to support our sensor network experimentation, which is Xscale. So in Xscale, we have around 1,000 XSM modes and 200 Stargates deployed in an area of 1 kilometer by 300 meters. Not only do we have the different types of hardware, software platforms, the application is also divided into multi-phase because of the resource constraint, such as so the phases would include things like localization, reprogramming, and the real sensing application logic. Also, given the uncertainty in the environment, network, or deployment, we usually need multiple levels of reconfiguration, such as simple parameter tuning, or the activation or deactivation of signal processing schemes, or the system level reprogramming. Since we don't have this experience of building large-scale networks before the Xscale, we decided to set up a testbed to help facilitate the design, development, and debugging, as well as deployment of the system. So the basic usage for the testbed for the Kansai is for at-scale validation of the middleware services for the application logic developed. In particular, we want to test the feasibility of reliable and real-time messaging in the large-scale networks, such as 802.11 networks of 200 nodes, which could have long routing hops, such as 15 to 30 hops. So to this end, we have configured the Kansai testbed such that it mimics the topology of the xScale deployment. Also, we tune the link level characteristics such that the performance we get for the messaging services and application logic would be similar to what we would get in the xScale. And similarly, we can extend this study into the envisioned final deployment, which would span around 10 kilometer by 1 kilometer space. And we have done some experiments, and we have seen that similar phenomena can be observed from the testbed to the field experiment at different scenarios. So moving forward, having the ability to perform experiment locally at the Kansai, we have developed a web interface to enable remote experimentation. This is used when we were actually in the field for the xScale experimentation, where we would find some integration bugs so that we can actually use a Kansai far away from where it sits, and using this simple interface to perform experimentation. So with that, we have the platform-specific. We have this platform-specific testbed. But then another step we took is to actually build the portable array such that we can collect environment data and embed, and then inject this environment data into this stationary array, which is more platform-specific, to study the overall system performance. Also, after studying the system performance and the system configuration, we can then use the experimental result to configure the field experiment, such as some filtering parameters. So right now we are evolving the set of portable arrays along different dimensions, such as the mode platform or the sensors. By this, we hope that we can sort of combine the benefits of this platform testbed and the domain testbed, such that you can study more efficiently the system-wise. So given that the number of platforms and the user usage scenarios are evolving, one critical component of the system is to actually monitor the system resource conditions and user usage scenario, and to facilitate the efficient operation of the whole system. For example, we have the component director, which can manage the network resource as well as facilitating the job creation and job orchestration, such that the users can use a testbed very efficiently. So one thing I'd like to mention is that we are trying to evolve in the orchestration tool to support a rich job control language, so that the users can perform their jobs by defining different jobs and then combine the jobs in different manners according to the logic they want. So looking forward, we are trying to build an integration environment to support the end-to-end application development, such as from the very beginning, from the application logic synthesis and to the composition, and then debugging or testing, etc. So we have some prototype running right now. So maybe offline, if you are interested, I can show you the web interface we have, and we can discuss more. So as of today, the Kansai is already openly available to the community. So you can just get an account and use our testbed to conduct remote experimentation. Or you can even combine the local testbed you have, and we can perform some cooperative experimentation. Also, we are developing tools that can enable the plug and play of other integration tools. So if you have some tools you want to get integrated in the system, we would like to try it out. But in order to make this happen, we need the users, the application developers, the tool developers, and platform developers to work together. And to make it work, we need define some common interface between the different application, different components of the architecture. And it's our thought that the users will drive this development because that's what they would need in the end. Of course, we are looking for any advice or involvement on this effort. Thanks.
Any questions for Homeway? My question is Anish's child a boy or a girl?
A boy.
Any other Yankee fans out there? This is a Red Sox fan, I'm sure. So I think the game started. So I want to thank Feng for inviting me. I feel like I'm representing the U.S. government. I'm the token gov guy, and I think this late in the day, it's you either have to have some compelling presentation or you have to have something funny to say. And I did have something funny. It was actually Stuart mentioned the valleys here in Washington. It reminded me of a great computer scientist, biology, mathematician joke. But since I can't speak that fast and I don't have that much time, I'm going to give up on that joke and I'll tell it at dinner at our table. But but I will. I do want to recollect something and give some context for some of the things that I heard today. And I think it was in Deborah's presentation, she had the history of sensor nets. And I noticed near the top, the DARPA packet radio test bed. And I had the unique privilege to participate as a field engineer when I was much younger in the packet radio test bed at Fort Bragg, North Carolina, where we had deployed the Collins Rockwell radios with an LSI 1102 processor connected to a terminal. And there was a lot of discussion at that time, Chris, and you'll appreciate this, whether or not we needed a base station for such a network, or whether it had to be sort of ad hoc. And Collins was coming up with different scenarios. But then it became very clear that if we didn't have the base station, we wouldn't have the connectivity to the PDP-11, thank you, and we wouldn't have no connectivity to the internet, such as it was, and how would we get to our TOPS 20 hosts to read mail? And that was the dull but compelling application. And today, most of you, some of you I'm sure, have a BlackBerry in your pocket. That's what we had, 25, 30 years ago. That's what we wanted. It took a 30-pound PDP-1123 to connect to the internet. It took a packet radio with an LSI 1102 that was about the size of this. But we didn't, it didn't really matter because it was research, it was science, it was fun, but it had an application, and the users that we had were thrilled about it. They said, hey, you're going to get scientists and engineers that are going to shrink that down. It's going to be on your wristwatch before you know it. And the thing that I learned there, and then 5 years later, we're in Heidelberg, Germany, to do another demonstration. And I'll tell you, Rockwell had really bright guys. And They had about 3 satellites up there, and they had this device called a global positioning system. And we had, for 2 hours a day, we could actually tell the location of that device. So we took the LSI 1102 out. We put a Sun workstation in there. We got a Honda generator, tied it to the back of a van. And we were able to track that van right around Heidelberg, driving all around. And we had it for a 2-hour window, but I tell you, the generals thought that was the greatest thing. And today, that GPS is in your handset, you know, for a E911 call. So I think the point here is that technology actually goes very fast. Commercialization doesn't go quite so fast. So I know if you're trying to get venture capital, you want to be able to show some application very quickly. And that's somewhat unfortunate because there's a lot of good research in this room that, trust me, 20 years from now, it's going to be like Ethernet in your home. Did you ever think that you would have Ethernet in your home? You did. Well, you see, now there's a visionary. That's a visionary. And we got it. So I want to talk very briefly, I know I don't have a lot of time, about what we're doing. And one last thing, Matt, you said, I think, that you weren't the philosopher, but in fact you are the philosopher. And all the questions that you're asking are exactly the right questions. And they need to be asked. And I think they give a wonderful context for the work that we're trying to do at Oak Ridge. For those who don't know, and I know Catlin does know, that we're a multi-science DOE lab, a government facility, Oak Ridge, Tennessee, the eastern part of the state. We are working for the Department of Defense as well as the Department of Homeland Security on a way of connecting sensors to the internet. And these are a specific breed of sensors: chemical, radiological sensors, meteorological sensors as well. And for those who have worked in the public safety sector, you know that most of the communications that's done are done on land mobile radio systems that are jurisdictional, and typically they don't connect to the internet. They don't connect to the next jurisdiction over. They're very much stovepipe networks, which makes it a very difficult problem for voice, and almost to have interconnectivity with data just doesn't exist. And this is the marketplace now for a lot of radiological portal monitors and chemical sensors that are being deployed in cities all over the country. So we're working on a SensorNet project with the Open Geospatial Consortium and with NIST and with OASIS to develop some simple, really trying to promote some really existing interoperability standards so that we can get these networks to work with each other, so that we can get applications that we can port from one jurisdiction to the next. And we've really, sort of answered the question, it sort of has to be on the internet. But we don't know yet how that happens. We know we need a plug and play. We need some dynamic kind of interface. And we're using IEEE 1451 for lack of anything else right now. I guess we could go with universal plug and play. That would do the self-identification. Ginny has a solution. Even the salutation protocol that Bluetooth uses could be used, but we're using 1451 because it was intended for sensors. Unfortunately, none of the sensors that we use implement 1451. There is this requirement in the middle for a service-oriented architecture that allows for discovery and directory services. The Department of Defense has an initiative called Net-Centric Enterprise Services. Department of Homeland Security has its own initiative. We're going to glom onto whatever that service-oriented architecture is in the middle. In the end, it might be what Microsoft specifies in its operating system. And then we're using OGC's SensorWeb enablement. And Matt, I would encourage you to look at the work that OGC is doing with SWE and its web feature services. And we've taken this, and actually we have implemented, it's sort of curious, this reality browser. This is, the precursor to Google Earth. It's what was called Keyhole or Earth Viewer at the time. And this is Fort Bragg, North Carolina. This is, we use a shim between our middleware stack that has the WFS, and we have some NOAA sensors deployed that give metadata. In some cases, we can show biological, radiological, or chemical, not on this particular map. and video. And you can basically click on your Google Earth, and that'll pop open a window, a browser window, and you can see the metadata. Or you can track Nextel phones. That, you know, Nextel is one of the vendors that exposes the GPS on their handset. So you can actually write a little Java applet, drop it in the phone, go through our middleware stack and look at that on one, you know, sort of reality browser. So that works. What we want to do, though, is take the different sensors that today come into the 911 center at Fort Bragg, and they go through some proprietary software that does a gateway function, and it's very expensive, a lot of software engineering to take the weather, the chemical and radiological sensors, the fire alarms. They have intrusion detection alarms for all their arms rooms, and they have an intelligent video system to do perimeter security. And all of these have custom interfaces and typically custom applications, and we just want to replace that with this middleware stack that has standards on either side, so that we can take these sensors sort of out of the equation without worrying about changing the rest of the architecture. When newer technology comes in, is available, we can pop that in, and everything's copacetic. So it's not really, I think, in fact, Deborah at the end said, well, this is not really research, this is an IETF issue. And that's exactly what we want it to be. And if we can get an RFC out that specifies this is what you use to connect to a 911 center with your sensor, that would be wonderful. It would be wonderful. So that's it. That's the extent of my discussion. Any questions? Bang.
Two comments. One is you mentioned IEEE in
1451.
Which is actually basically a device discovery protocol that reads a certain section of the memory of the device.
Right.
Which is useful for discovering devices. But I think what you actually want, the interfaces, is actually more about discovering the service capabilities of different sensors, which is the higher level of device discovery.
Right.
And I think that this actually goes probably related to some of the things that Dee was talking about, is that if you think about it, these are providers of services. You need to have some standard way of describing the services.
Exactly. Exactly. So 1451 gets us through the physical, up into a data link, up into the network. But then, you know, where's the UDDI or whatever it is that's going to be in the service? And definitely, we think that's going to be dictated a lot by the organization or the agencies that deploy it. But yes.
The other one is that your reality browser, a very nice example. Can I actually index and search for things?
Pardon?
Can I search for
Oh, no. Well, give Google another 6 months. You got to look at today's New York Times. They got a great, in the op-ed page, they got a great cartoon with Google 2086, and they show you the Google portal. Take a look at it. It's a great, you can search your mind. It's very funny.
One more question if there is one.
Thank you.
Thanks a lot, Brian.
Thank you.
So last but not least today is our good friend Prabal Dutta from Berkeley, and he's a special bonus I thought we managed to squeeze in right at the end of the other 8-minute talk. So Prabal.
So can you hear me okay? Great. I understand I'm the only thing that stands between you and dinner, so I'll try to make this quick. But I do want to end the day with a big picture point, and that is we heard a lot about the research that's happened and the industrial work that's happened to enable academically dull applications. However, we heard a lot about $400 million projects to pepper the landscape, the ecological landscape, with sensors as well. And so there's a little bit of a chasm between buildings and the entire U.S. And what I'm going to talk about today is one small piece along that spectrum. So I'll be talking a little bit about work we did at Berkeley this summer. This was the NEST final evaluation for the DARPA NEST program. And really, the motivation for the testbed you'll hear about was a multi-target tracking application, but that was the stuff the EEs were doing. The CS folks were interested in building large-scale, long-lived outdoor testbeds supporting systems research. We've heard a lot about applications research, but take a look at some of the systems research. So earlier large-scale testbeds were generally carefully designed, deployed, managed, and controlled. So I couldn't just run my applications on somebody else's testbed. There was a lot of engineering to make sure that the lifetime requirements would be met, so on and so forth. However, this favored safety and predictability. You wanted to know how your sensor network was going to act. You wanted to make sure you could collect the data you wanted because that's what was important. But it also sacrificed flexibility and experimentation in the systems levels. I want to try different networking protocols. Maybe Chris hasn't found the perfect solution for all applications. And this ended up leading to generally successful application deployments, but unfortunately a poor exploration of the computer science issues in large-scale networks. So what did we need to actually build a large-scale sensor network that we could just put out there? Well, we thought there were really two fundamental issues, sustainability and scalability. And by sustainability, what I mean is robust, long-term operation. We can put it out there and just let it run. We don't have to worry about lifetime issues. We don't have to worry about reprogramming and screwing up the network because we'll eventually get it back. And really, that enables flexibility and experimentation. So we want to operate on ambient energy sources. We want to use solar harvesting. But what if we want to experiment with different algorithms for charging? There might be different algorithms that are applicable. Some might preserve battery life by charging less frequently. But if you screw that up in your 1,000-node network, guys, now you're in a world of trouble. So we needed to make sure we could be robust about recovering that as well. So this means we had to build management and robustness in from absolutely the foundations up, from the very lowest level functionality at the levels of watchdog timers, grenade timers, all the way up. And scalability is the other important issue. 10 nodes, easy to deploy. 100 nodes, it's not too bad, but it takes a day maybe. But if you want really large-scale networks, you need to deploy them quickly with an effort that is probably proportional to the number of nodes. And here's the really tricky one. You need to operate it with near constant effort, independent of a lot of different variables. So a large number of nodes, anywhere from tens, hundreds, thousands. You can't have the level of effort required growing proportionally, because if you don't have sort of diminishing false alarm rates, you won't be able to scale these things. For example, across a range of densities, across a range of activity levels. And so the way to do this is to do it the way we do everything else when it comes to scale hierarchy. And this work ends up benefiting both the research and commercial applications. So you might ask, well, what happens if you have unsustainable and unscalable work? Well, it turns out you can spend an awful lot of grad student hours doing things like replacing batteries and reprogramming sensor nodes. That's a whole bunch of us getting ready to basically reprogram and change batteries on a 64-node extreme scale moat network. And we were not happy about this, but we did it because our program manager asked. In contrast, in about the same time, maybe a factor of 2 difference, we ended up deploying a 557-node network over a 50,000 square meter area in about 2 days, give or take maybe twice as long as reprogramming and putting batteries in that XSM set of nodes I was telling you about. We were collecting about 50 megabytes of data per day out of the sensor network, gave us great transparency, great visibility into what was going on. And we had between a 3 and 10 hop network. If we took down all of the levels of hierarchy, we ended up at 10 nodes. If we left them in, we ended up with a 2 or 3 node network. And it's been running continuously since August 27th. So what does that look like? Well, we had a whole bunch of service components. And I don't want to spend a lot of time in this, but the key message from this is when TinyOS started 5 years ago, the reason Chris complained earlier about there was nothing stable, there was no service, there was no API, stuff was changing. Well, there was a reason for that. we didn't know where to draw the boxes. Nobody knew. Nobody knew what the right services were. And now, after 5 years, people have a much better idea. And so we can imagine different profiles, different application profiles, different combinations of components that allow us to actually solve specific sets of problems, maybe event detection, data collection, so on and so forth. So I mentioned hierarchy a little bit earlier. Well, our network of 557 nodes look like the one you see here, are sort of our lowest tier of nodes, and we used an 802.11 network to give us long range. Now, it turns out that the 802.11 network was a lot harder to get working reliably than our moat network, which really surprised us. And we had a couple of IT folks working on the 802.11 network. Maybe we should have used RoofNet or something. I don't know. There's been an interesting sort of divergence and convergence in the hardware platform. So about 2 years ago, the Mica 2 moat from Crossbow was kind of the state of the art. And that sort of diverged. And at Berkeley, we took sort of the push the envelope approach. We pushed power, we pushed different radios, so on and so forth. The middle of that, the Mica Z, was trying to maintain backward compatibility through interfaces and processor, yet try different radios. And at OSU, where as a grad student, before I came to Berkeley, we were trying to minimize risk by sort of bringing the processor and radio forward from the Mica 2, but innovating on the sensor platform. And so when we had an opportunity to rebuild a network, a node from the ground up for this final experiment, we sort of pulled in all of those pieces and tried to do sort of a best of breed, and again, push the sustainability and scalability aspects of it. So we ended up building a new open experimental platform. And the key part of this is that we were able to go back to these numbers again. We ended up deploying 557 nodes in a couple of days. That's about the closest that we've come to just throwing nodes out there. And we sort of punted on the hard problems, so we solved the hard problems by making them simple. Rather than trying to solve localization, we just got a first year and put a backpack and a differential GPS on his back and had him go around and tag the moat. And he'd sort of have a yardstick and he'd kind of tag, he had a whole bunch of little barcodes that would sort of, he'd click on the barcode, that would tell him how high off the ground it was, and the node had a barcode. He'd click on that, it'd go into his desktop and got put into a database. The node was updated, and that database is what gave you the picture you saw with all those little green dots earlier. That was all generated from this database. So that's kind of the direction we're trying to go, trying to build these very large-scale networks and just seeing how we can explore the computer science issues. The applications are great, but let's not forget there are some computer science issues. And after all, Mark Weiser was interested in finding out some of the answers to those questions as well. Thanks very much.
Prabal, quick question.
Yeah.
So it's been up and running since end of August. Is there any plan to leave it running, or how long do you plan to leave it running? And secondly, is there any plan to possibly open it up and make it accessible for the rest of the community to use?
So yes, we'd like to keep it running as long as possible. Turns out environmentalists are also interested in the area. We have autonomous helicopters flying around. So we're losing nodes. Some of them get destroyed, but we're trying to keep them up as long as we can. And the second question is, yes, we're making it available on sort of a select basis because the people who develop that network are using it for their dissertation work as well. So we can fit people in between that. Yeah?
So given that it's a hierarchy, then there's actually, you can think of it as a bunch of different networks.
Not really. So the hierarchy is just in forwarding. There's not processing at the hierarchy level. So it's really a two-hop network in terms of data processing. It's more than 2 hops if you just look at the forwarding.
What is the error rate? And what's the combined error rate? You've been up for a couple months now.
I actually don't know that. We have
Somebody knows.
Yes, somebody can figure it out. The thing is, we're using radios that will give us link quality indication, but they won't tell us the exact error rates. I mean, if you're talking about error packet bit errors that get through, or what?
Each node's trying to do something, And the question is, what's the success rate?
So you mean, for example, how many times do expected number of transmissions to get a packet through or something like that?
Yeah, or overall or other.
Right. So we have a whole bunch of experiments going on this. We're doing localization, networking, data collection, dissemination, reprogramming, and then there's, of course, a bunch of applications running on top of it. But those are the kind of questions we're trying to answer with this network. Right. Thanks very much.
Thanks, Prabal. Thanks. Going to just talk about the order of tomorrow's proceedings, and I'll close with the logistical things.
All right. So I just want to actually spend a minute summarize a little bit about some of the things we heard today. There's a lot of things we actually had heard. And we couldn't get everyone to present, but we have a pretty good section of people who were able to present. We heard about the Euro modes, the Intel modes, the Berkeley modes, smart dust, brilliant rock, soil applications. I can name a few of them. Actually, there's a toilet application, $1 million fab application, volcanoes, and so on. We argued about actually the need to build vertical applications to really understand the application space, but we also argued about maybe we should actually build these horizontals sometimes that will allow us to be able to reuse a lot of these different components. And I think there's a lot of stuff going on, and we should let this to sink in and over the dinner and sleep. So tomorrow we're going to talk about this in these three different discussion groups. Here's my first cut on the three different groups, and I have asked Ralph to be the lead for the platforms and the platforms application group, Mike Franklin to be the lead for the services group, and Jianfeng to be the foundation group lead. If you feel like you'd rather be in a different group, that's very flexible, but just let the group lead or me know so that we know that how to balance the load a little bit. Anyway, with this, I will hand over to. By the way, two quick things. Tony Hay is going to give a keynote tomorrow morning, and his talk title is E-Science, Cyber Infrastructures, and Sensor Nets. And in about an hour and a half, Dan Ling, who is sitting back there, Dan is in charge of the Microsoft research in Redmond, and he's going to host the opening day banquet, which I believe is going to be in this room, right? Yeah. All right, Stu, with that.
Thank you, Dave. So please, we allocated the schedule the next hour for pondering on the day and interacting, discussing on amongst